Hi guys, welcome back to our lecture on scalars and vectors. And again, as I have done in the first lecture, I'll be using the slide I found in slideshare.net by Khan Saif. You can also visit that site and see for yourself. You can also download the slides and study it again. So let's now continue with the lecture. We left the last lecture with vector addition analytical method. So here, last time we had we added vector q and p. So we have p here and in this direction and q in this direction. If we add them, we have to connect the tail of q to the head of p. So here you have that one, and so the resultant would be this one. If you review the calculation, you will see that the r here, by the way, the angle between q and p is theta, is the same theta here. The angle between them is theta, so the resultant is given by that, and that's actually called cosine law. So r is the resultant, p is one of the vectors, and q is the other vector. This one is the middle term of the expression. So the direction of the resultant, of course, this is now alpha. This is alpha. This is the angle between the horizontal line and the direction of the resultant. This is, when you say alpha, this is also the same as alpha degrees north of east, or you can say 90 minus alpha east of north. You can also say that. So, and we found that, so you can review the previous lecture. I will not discuss anymore how these are being done. Alpha can be derived using this, or you can follow the calculation. So alpha is just equal to the tangent inverse of q sine theta. Sine theta there is the sine of the angle between q and p. Q sine theta over p plus q cosine theta. So anyway, this is as an example. You have case 1, vectors p and q to be parallel. This means theta is 0. So theta is 0. So I just write theta equal to 0 degrees. So you have p and q. How do you do that? So you just use the formula for the magnitude. We have r equals p squared plus 2pq cosine 0 plus q squared. So cosine 0 will just be equal to 1, and you can factor this out. It's just p plus q squared, and r would be just p plus q. So how about the angle? The angle alpha. The angle alpha would be q sine 0, which is 0. So 0 over anything would be 0. So tangent alpha would be 0. So what is tangent alpha is 0? What does that mean? Alpha means also is 0. So that's it. It's 0 degrees with respect to the positive x-axis. So it's in the same direction as P and Q. R is in the same direction as P and Q. For case 2, where the vectors are perpendicular, in this case, your theta would be 90 degrees. So you can just substitute 90 degrees in the formula for the magnitude here, this one, and then you get R is equal to P squared plus Q squared, because cosine of 90 here is equal to 0, so the middle term is 0. Everything is 0 there. So you only are left with the two terms, P squared and Q squared. So your R will just be P squared plus Q squared. So the direction now would be Q sine 90 over P plus Q cosine 90. This is equal to P over P plus 0, because cosine 90 is of course equal to 0. So your tangent alpha is equal to Q over P, or your alpha is tangent inverse of Q over P. Now this is now alpha. This is alpha is above the positive x axis. That is your alpha. And how about if your Q is, if P is positive, going here P, and your Q is negative, what is your alpha? Alpha would be measured that way. So that's alpha degrees south of east or you can say negative alpha degrees. This means that you are below, you're measuring below the positive x-axis, or you can say that this is alpha degrees below negative x-axis. You can also say that. So look at this. If you try to look at this, this is a right triangle. You have P here and Q here. This is a right triangle, and R is here. So it's just the Pythagorean theorem, so that you have P squared plus Q squared is equal to R squared. That's for right triangles, only for right triangles. For other triangles, this does not work. You have to follow this. In general, this one is to be followed. Only for right triangles that you have to do this one. So how about when P and Q are both negative? So if you have P is negative, P is this one here, and then Q would be going this one, this is negative Q. So your alpha will be measured here, going here. So what is that? Alpha. So alpha is alpha degrees below negative x-axis, or you can say negative alpha Or you can say alpha south of west. That is the direction. Or alpha degrees, I mean. And how about when P is negative and Q is positive? When P is negative, you have to write the direction here, negative P. And then, of course, you have Q, positive Q, positive Q. So alpha would be measured here. And this is, the direction is north of west. So remember, the signs are also important. So when you say it's going to the right, by convention, that's positive. If it's going to the left, the convention is it's negative. If it's going up, the convention is that the direction is positive, and going down is negative, and going towards you is also positive, and going away from you is also negative. So that's the convention. So remember that. So how about when the vectors are anti-parallel? So it's just easy. You actually don't have to care for using this formula. You just directly add P plus the negative of Q. So that's just the magnitude. And then of course the angle would just be 0. Would just be 0 with the x-axis. So if P is greater than if P is greater than Q, then R would be that way. If P is less than Q, then R would be this way. So anyway, that's both 0 with the horizontal. Or you can say 0, or if it's in this direction and you're measuring the angle here, that's 180 degrees. It's the same. Or negative 180 degrees. It doesn't matter. For as long as you know the orientation, that's all right. Now, here's a very important tool in vectors. We call it the unit vector. It's a vector that has magnitude of 1. So anything that you multiply with that vector carries the direction of the unit vector. So for example, here you have a vector A. You have vector A, and the unit vector there is A hat, and it has a magnitude of 1. So, and of course the A and A hat here is equal to, I mean, the directions are both the same. So in this case you have vector A can be written as the magnitude A times the unit vector A. Remember, this is magnitude 1, so if you multiply this with A, it gives you A. So the vector, unit vector, lacks the dimension, so it has no unit. I mean, the dimension would be just any dimension would do, and the unit is also gone. So if A has a unit of meters per second, for example, you can carry the unit meters per second. The only purpose of the unit vector is to specify a direction in space. So let's go further. So A here is the magnitude, and A hat is the unit vector along A. So they have the same direction. In the Cartesian coordinate system, you have x, y, z axis. For the positive x, you have I here, and this is the unit vector, and then going to the negative x-axis is negative I. Going to the positive z-axis is positive k, and negative k-axis is negative k, and then positive y-axis is positive j, and to the negative y-axis is negative j, and that's the convention of the unit vectors in Cartesian coordinate system. So you can use the direction if you say put 3i, this means that you're moving, or you're in the positive axis. That's 3 units from x equal to 0. So if you have negative 3i, this is also equal to 3 negative I. This means that you are on the negative x-axis. The same goes true for j and k. So now, so if you have a vector A here, so if you want to get the component of the vector on axis t, so for example this is axis t, then you'll just have to get the component of A on axis t. So you have to get the projection of A on t. And also if you have n, then you have a projection of A on n here. So in that case, you can write A equal to an plus, or an plus at t. These are the unit vectors on on this axis, and the unit vector t is on this axis. So anyway, let's not complicate ourselves. We just use the xyz coordinate system. So for example, if you have a two-dimensional vector, meaning it lies on a plane, you have A here, you have A on this vector, so it has a projection on x here, and then you have a projection also of A on the y-axis here. So both AX and AY are positive because they are located and they are projected in the positive x-axis and the positive y-axis. So you have AYJ and AXI. So you can write the A in terms of AX and AY in terms of the I and J unit vectors. So that's how you write the unit vectors in Cartesian coordinates, and this is used commonly in writing vectors. Of course, you can write the vector in different coordinate system, but mostly we use Cartesian coordinate system in solving problems in physics. So this is how you get the angle. So you have ax, the component of a along the x, and the component of a along the y. The angle a, the direction of a, is you can either use this sine theta is ay over a. So if you know ay and you know a, you can get the theta. That's just arc sine of ay over a. Or you can also use this, because this is the cosine. The component of a along x is just the cosine of a. So you have this, you have ay is equal to a sine theta, and ax is equal to a cosine theta. By the way, this is a right triangle. So this is just a square plus ay square is equal to a square by Pythagorean theorem. If you know that is a right triangle, then you can automatically use that. You can automatically use that formula, the Pythagorean theorem. So I would say that ay square is equal to ay plus ax square is equal to a square sine square theta plus a square cosine square theta. This is equal to a square times sine square theta plus cosine square theta. What is cosine square theta plus sine square theta? That's just equal to 1. So you have a square. So next time I have to write more legibly. So you have for the components you have so you can write the vector like that. So again, I've just told you earlier that the magnitude is just the square root of x squared plus ay squared, and then the direction is, of course, tangent inverse of, or arctangent inverse of, or arctan, sorry, just arctan ay over ax. So if you have a three-dimensional vector, then it has a component on the x, it has a component on the y, and on the z. So that vector is located in, not in a plane, but in a space, a three-dimensional space. So it has ax, ay, and az. So you can sum ax, ay, and az, and then you can also write in terms of the unit vectors this way: axi plus ayj plus azk. So how do you get the angle between a and the x-axis? So you just get cosine equals ax over a. It's a projection of a on the x-axis, so your ax would be this one. So this is alpha, and of course the orientation on the y-axis would be different, so you have a different angle. So cosine beta would be ay over a. So ay is just equal to a cosine beta, this one. And then for the z-axis, you have az equals a cosine gamma. So you have a different direction. You can so your a is located in space, and it's some angles with respect to xyz axis. So you have alpha, beta. These are the directions. These are the direction cosines of the vector. Direction cosines. And the magnitude is, that's so familiar, that's just the three-dimensional generalization of the Pythagorean theorem. So that's it. And then you have as I've said, you can write the vector like that. So how do you add vectors by components? So you have an x component, a y component, and a z component of the vector. So if you have two vectors a and b, and you have to get the sum, then you just add the corresponding component. So you have to add the corresponding components. So the resultant would be, this is r. So this is ax plus bx, ay plus by, az plus bz, and then you have of course the magnitude there. What is the magnitude? So let's the magnitude would be r square, or okay, r squared, this is ax plus by bx square, plus the same thing for y, plus the same thing for z. You just write ay plus by square plus az plus bz for the third term, square also. So this is your x component of the resultant, the y component of the resultant, and then the z component of the resultant. So how do you multiply vectors? You can multiply vectors by a scalar s, and you get a vector that is the same direction as the original. And if you multiply by s greater than 1, the resulting vector would be longer. If you multiply s less than 1, the vector less than 0, greater than 0, less than 1, the resulting vector would be in the same direction as the original, but shorter than the original. If the s is less than 0, negative, then the direction would change opposite to the original. So here you have s is positive, so you have here the same direction, and s is negative, you have an opposite direction. There are two ways to multiply a vector by a vector. You can use the dot product and the cross product. The dot product is a scalar product. It means that it has no direction, and the other one is a vector product. The product is a vector and has a direction. So the scalar product is A dot B, this is defined as AB cosine theta. And the angle theta here would be the smallest angle between A and B. Do not use this angle. This is a wrong angle. You have to use only the smallest angle here, theta. So how is that done? By the way, examples of a scalar product are work and power. So a vector F, or force, is dotted to a displacement S. We will know what is a displacement in the following lectures. So work would be F dot S. This is force times the displacement cosine theta. This is the angle between force and the displacement. And of course, you also have power. This is force dot to a velocity. So power is force dot to a velocity. Or ordinarily you can say power is force times velocity, but actually you're operating a dot, not an ordinary multiplication. Ordinary multiplication is only for ordinary numbers, not for vectors. So the dot product can be regarded as a product of two quantities, the magnitude of one of the vectors. The scalar components of the second vector are along the direction of the first vector. So let's look at the figure. So this is A dot B. So if you have A here and then B is here, so what is B cosine theta? B cosine theta is the projection of B along A. So you can get the product A without the arrow above. Without the arrow above is just the magnitude of A, vector A. Or B without the arrow above is just the magnitude of vector B. And here you have A cosine theta as the component of A along B. So that's that product. You multiply the component of the other vector along the first vector. The scalar product is commutative, meaning you can interchange the two vectors. So this is A dot B is AB cosine theta, and B dot A is BA cosine theta, but this is also equal to AB cosine theta. So therefore this is equal to that. So meaning A dot B is equal to B dot A. It doesn't matter. Also, the scalar product is distributive over addition. So if you dot a vector A to a vector sum, then it's the same as dotting A individually to the two vectors that were summed. Or you can say that the dot product to a sum is the sum of the dot products. So this one. And the scalar product of two perpendicular vectors is equal to 0 because cosine 90 is 0. So if you have two perpendicular vectors, you get the scalar product that's equal to 0. If you get the scalar product of two parallel vectors, then that would be just the product of the magnitude, because cosine 0 is equal to 1. this is equal to 1. For two antiparallel vectors, the angle between them is, because if you have antiparallel, one vector would be here and the other vector would be here, and so the angle is 180, and the cosine of 180 is equal to -1. So the scalar product of two antiparallel vectors is negative, and this is just equal to the negative of the product of the magnitude of A and the magnitude of B. The product of a vector with itself, of course, a vector is parallel with itself, so cosine 0 is on the works there, so this is equal to 1, so that's just A square. So how can you what do you say? A square is equal to AX square plus AY square plus AZ square. This is also equal to A dot A. Remember, when you write the vector with arrow, it's different from this one without the arrow. This is ordinary number, and this one has direction. The one with arrow has direction, and this one is ordinary magnitude. So let's look at the vector, the unit vector, the dot product of the unit vector. So I dot I, this is parallel. J and J is also parallel. So this is 1, cosine 0 equals to 1. But if you dot I with J, or J with K, or K with I, this is 1 times 1 cosine 90. That's cosine 90 is equal to 0, so everything is 0. So the unit vectors, so if you have two unit vectors that are in the same direction, you get 1. If it's anti-parallel, say for example negative I dotted to I, that's -1, of course. And so if you get the dot product of two vectors A and B with these components, so you have to multiply the components algebraically. So if you do that, you will have 9 terms. This I dot I would be equal to 1, and J dot J would be equal to 1. Would be equal to 1, and K dot K would be equal to 1. And I dot J would be 0, and I dot K would be 0. J dot I would be 0, J dot K would be 0, K dot I would be 0, and K dot J would be 0. So what's left? So what's left is only this, and this. So therefore, your A dot B is equal to this one. Remember, it doesn't have direction, so scalar product or the dot product has no direction. So remember that always, because you might make a mistake in solving problems later on. This is also equal to AB cosine theta. So you can find the angle between the two vectors if you use this formula. So there's a vector product. If you have two vectors, you use your right hand to get the direction. By convention, you use your right hand to get the direction. So if you say A cross B, you put your palm on A and then move A towards B, and your thumb will give you the direction of the vector product. So the vector product is AB sine theta, but it has a direction. The scalar product doesn't have direction. So AB sine theta, you have a direction here, and this is a vector. So that's why it's called a vector product, because the product is a vector. So this is how you do it. So you have A, put your palm on A and then move your palm towards B, so you get the direction C by your thumb. So this is your C, the cross product, and your thumb is in that way. Examples of vector product are torque or angular momentum. Later on you will study about torque and angular momentum. So this is R cross F, and this is R cross momentum cross P. So those are just examples of how the operation is used in solving for some quantities in physics. So what is the geometrical meaning of vector product? So here you look at this. This is a vector A and this is a vector B with angle theta here. The component of B along A is this way. This is B cosine theta, and of course this is B sine theta. B sine theta. This one is the component of A along B is A sine theta. But this one is, oh sorry, this is A cosine theta. This one is A sine theta. A sine theta. So as you can see, if you multiply this, if you multiply this one, if you reorient this, you multiply this one and this one, it gives you the area of this parallelogram. You can see it better here. So if you multiply B and A sine theta, this is just the area. This is the formula of the area of the parallelogram. This is the base times the height of the parallelogram. And of course this is not a triangle. A triangle has 1/2, so that's the area of a parallelogram. So the cross product has a magnitude of the area of the parallelogram that is made from the two vectors A and B, for example. So A cross B. Earlier we had A dot B is equal to B dot A for the scalar product, and this is commutative. But in the case of a vector product, A cross B is not equal to B cross A. This is equal to negative B cross A. As you can see, this is AB sine, this is AB sine. It has a negative sign in front. So the vector product is not commutative or anti-commutative. However, it is distributive over addition. So you can distribute A to the sum of two vectors. This is the magnitude. So if two vectors are perpendicular, that is sine 90, the angle between them is 90, so your magnitude of the cross product is maximum AB. But if you get the dot product of two perpendicular vectors, the dot product AB is always equal to 0. This one is the absolute sign here signifies that this is magnitude. The direction is neglected, but A cross B always has a direction. This is a vector. This is a vector. This is a scalar, no direction. No direction for that. Vector product of two parallel vectors is a null vector. So if you have a parallel vector, so if A is crossed with itself, that's the angle between them is 0, so sine 0 is equal to 0. So that means that you cannot move A towards A. You cannot make a motion, so therefore the vector product is equal to 0. So in this case, A and B are parallel. You cannot make a motion of A going to B, or you cannot make a motion of B going to A, or you cannot move them, so that's equal to 0 if they are parallel. But if they're perpendicular, that's maximum vector product, the magnitude. So always remember that there's a unit vector n here. It depends. N could be I, n could be j, n could be k. If you put the absolute value here, then you will have to erase the n. But if you don't put there, you have to put n. So you have two anti-parallel vectors. This is just the angle between them is 180. Again, sine of 180 is equal to 0. So for anti-parallel vectors, you have A cross B is equal to 0 for anti-parallel. For vectors with itself, also 0, because the angle between them is of course 0. And then for vector products, you have I cross I, j cross j, and k cross k would be 0. Would be 0 because the angle between them is 0. But for if you use your right hand, I cross j would be k. So this is I, j, and k here. So if you use your right hand, you put your palm on I and then rotate or move your palm towards j. That will give you the direction k. If you're doing the reverse, you put your palm on the j and then you put your palm on the j and you move your palm to I. It gives you the negative k direction. So that's what it's written here. So you can experiment with your using your right hand. So this is just to aid your memorization of the of the direction. So if you're crossing I to J, it will give you K. If you're crossing J to K, it will give you I. And if you're crossing J to K, it will give you J. I mean K to I will give you J. But if you're crossing J to I, it will give you negative K. And then if you're crossing I to K, it will give you negative J. And if you're crossing K to J, it will give you negative I. For this one, it's positive. So here you can get the vector product of two vectors. Again, you have to multiply everything. You have the components of A, the components of B. You will get, if you multiply everything, you will get 9 components. 2, 3, 4, 5, 6, 7, 8, 9. And for this one, I cross I is equal to 0. I cross I is equal to 0. J cross J is also equal to 0, and K cross K is equal to 0. I cross J is equal to K. I cross K is equal to negative J. This is negative J. J cross I would be negative K. This is negative K. And then J cross K would be negative I. And K cross I would be negative, K cross I would be J. K cross J is negative I. This is, by the way, positive I. Sorry, I made a mistake. And so you're left with 6 terms. You're left with 6 terms. This one, this one, this one, and that one. And so you will have. In simplifying it, you will have this one with unit vector I as a direction, and this one with unit vector J as a direction, and this one with unit vector K as a direction. So if you write it in matrix form, it's just equal to this. This is if you get the determinant of this matrix, the determinant of this matrix is equal to this expression. So that's how you do the cross product. Remember, the dot product A B is equal to AX BX plus AY BY plus AZ BZ. No direction here. No direction. It's purely scalar. No direction. But for A cross B, you have the direction. You have the direction I, J, and K. By the way, the middle term is negative. So that's the cross product. So that's it for the lectures for scalar and vectors, and I hope you've learned something. The next topic would be, but before we go to the next topic, maybe I'll give an example to you on next meeting. In the following meeting.